We are at the final part of our lesson 43. Lesson 43 is part 3 is about making predictions using our regression line and whether or not those predictions are appropriate. So what we have learned so far is how to find the regression line using our calculator, how to interpret slope and y-intercept in our regression line, And now this last part is using our regression line to predict values and whether or not those predictions are appropriate. So the first task in this lesson is to predict the price when miles driven is 80,000. So they want us to plug in x equals 80,000. I'm just finding my marker. So next to this problem, I'm going to write x equals 80,000. So to find the predicted price, we do y hat equals 38257 minus 0.16, and we're going to plug in 80,000 for x. So a couple things to note here. You do need to say y hat equals, that has to be there. The other thing worth noting is that on your quiz that goes along with this lesson that's down below, you are told to show work when calculating a value. This that I'm highlighting is what they mean by show work. They want you to show that you are plugging 80,000 into the linear regression equation. So they don't just want y hat equals whatever this equals. They want to see the work that goes with it. When you plug this in, you get 25,457. So using the data that we observed, we can predict that a truck with 80,000 miles will cost about $25,457. So now the question is, how do we know if it's appropriate to use our regression line to predict a value? So in this case, we used it to predict price at 80,000 miles. The next question says, should we predict the price when the miles driven is 180,000 miles? Now, we definitely can. We can plug 180,000 in there, but it's not necessarily going to be a good idea. And the reason why is shown in the pictures down at the bottom of this note sheet. I took these from the AP board, the videos that the AP board releases. And this is talking about an idea called extrapolation. So the setup here is, using linear regression, a widely cited study concluded that by 2048, if trends continue, 100% of Americans would be overweight. So in about 50 years, all of us would be considered overweight. Using the graphs below, do you believe that 100% of Americans will be overweight by 2048? Why or why not? So what we can see here is that we have collected data on the percent of the U.S. population that is overweight from, it looks like, about 1978 to about 2005. So between 1978 and 2005, this is the percent of our nation that is overweight. And as you can see, it's steadily increasing. So now if we project that line even further, so if you notice your x-axis down here, we have the years continuing all the way up to 2050. And as you can see, at 2050, we're at 100% of us are overweight. The issue, though, is we don't have data, we don't have any observed data past about 2004. This data stops in the 2000s, and they've indicated that by putting that dotted line there. Sorry, I was trying to zoom in. So we're predicting something that is outside of what we actually have data for. I'm going to say that one more time. We're predicting a value for a year that we do not have data for. We only have data up until about 2004, but we're going to make a prediction for the year 2048. That's not a good idea. So predictions made outside of the interval of our current x values is extrapolation. And the reason why that's not a good idea is because we don't know if that straight line continues past what we have observed. From here, from the last year recorded, this line may start to curve. It may start to decline. We don't know for sure that the trend or the linear pattern continues past the years that we have collected data for, which would make sense because we've seen some data sets where it looks in a certain area, it looks linear, and then as the data moves on, it starts to take a curve. So I'm going to say that one more time, but make myself a little bit bigger. So we've seen data sets where on the lower end of the x values, we see a clear linear trend, and then all of a sudden it starts to curve. We also have seen data sets like where the ball is thrown into the air, or the gas mileage problem, where if we looked at only one part of the graph, it looks like a positive linear relationship, and then it turns down into a negative linear relationship. So the biggest takeaway from these pictures down at the bottom of our note sheet is that we really only have reliable predictions for the x values we observed. We really only have data here for 1978 to 2004, so only predictions within that window are going to be reliable. We can only predict the percent of our population that is overweight between the years 1978 and 2004 because that is the only time period we actually have data on. We do not want to make predictions for data that is outside of the observed values that we have because we don't know what happens for those x values. We only have an idea about what happens for these ones. So going back to our graph for our trucks and our price, our miles driven and our price, we have collected data for cars between miles driven. It looks like the lowest is 4447 and the highest is 144,162, I believe. So I'm going to highlight those. Lowest looks to be about 4,500. Highest is 145. We should not predict a price for any trucks that were driven less than 4,000 miles or more than 145,000 miles because we only have data on trucks that have been driven from about 4,500 to about 145,000. So our first prediction is okay. The prediction that we made for 80,000 miles, that is a reliable prediction. So I maybe should make a note next to that just for my own reference that this prediction is reliable. Sorry, my pencil's not very happy with me. This prediction is reliable. This prediction is not reliable. We absolutely should not predict the price when the miles driven is 180,000. So no. And once again, we're at a sentence or a phrase to memorize, and that is down here. You're going to want to follow this template for your answers. So, no, we only have data for trucks with, okay, down here it tells me I have to write my explanatory variable there. So, for trucks with miles driven, so recall that's what is on my x-axis, between the observed values, and then I highlighted them for us, 4, 4, 4, 7, and 1, 4, sorry, I forgot the word and there, and 1, 4, 4, 1, 6, 2. So no, we should not do this because we only have data for trucks with miles driven between 4,447 and 144,162. So we would be extrapolating. We would be extrapolating. If you're at home, you should practice saying that word. Extrapolation or extrapolate. We would be extrapolating because 180,000 is outside of the interval we listed. So no, we only have data for trucks with miles driven between the observed values, and then I give the values. So we would be extrapolating because 180,000 is outside of the interval that I actually have data for. We don't know if the linear pattern will continue beyond, so they're giving us a value that is too high. So let's go back and figure out what our maximum value is, because I highlighted our min. What is our max? 144,162. So we don't know if the linear pattern will continue beyond 144,162 miles driven. So the idea here is we can make predictions with our regression line, but we need to be very careful because we can only make predictions for values that are within the data that we have observations for. Anything outside of the X values we observed is not allowed. It's called extrapolation. Extrapolation, for our definition right here, is the use of regression line for prediction outside the interval of values of the explanatory variable used to obtain the line. Remember, explanatory variable is the X or x-axis. And then this last statement in our text box is very important. Such predictions are not accurate. We've also used the word here, not reliable. And then before we move on, let's just make sure that we have everything in our phrases to memorize. One thing that we do need to add in is this last sentence. We don't know if the linear pattern will continue beyond. It might be the largest X value or the smallest X value, depending on what they're asking you to predict. So normally when you do problems about extrapolation, it's going to ask you, should we use our model to predict this value? And in response, you would say, no, we only have data for what blah, blah, blah. So we would be extrapolating, and you use this as your sentence frame. So before we move on, let's just take a quick look back at everything we've discussed in this lesson. We have how do we find our regression line? How do we interpret the different elements of our regression line? And then what values should we use our regression line on or for? Lots of phrases to memorize in this lesson. The next page is a problem that I think we should do last. So at this point, I want you to go to the back page, and I want you to do the two problems on the back page. I want you to ignore the table at the bottom. That was my bad. You don't need that table there. So I want you to pause the video, and I want you to try number 2 and number 3. When you're ready, come back and we'll check answers together. Okay, I want to start with number 3 because that's the easier one to me. Hopefully you practice showing work. So y hat equals 1.8 minus 0.2 times 5. You plug all of that into your calculator. You get 0.8 or delta. Now this top one had me stumped for a minute. So a family would like to build a linear regression equation to predict the amount of grain harvested per acre of land on their farm. They subdivide their land into several smaller plots of land for testing and would like to select an explanatory variable they can control. So I knew when I first read this problem that that was an important statement. We have to choose a variable that we can control. Which of the following is an appropriate explanatory variable that the family could use to create a linear regression equation? Okay, so the amount of rainfall recorded at their farm. I automatically knew it wasn't that one because we can't control rainfall. The type of crop planted in the plot. Well, yeah, we can control this. So this one was a can't control. This one is a can control. Okay, well, the average daily temperature. No, we cannot control temperature unless this is like a crop in a greenhouse, but it's not. D, the variety of grain planted. Well, yeah, we can control that. And then E, the amount of fertilizer. Well, yeah, we can control that. So then I was very stumped because I thought, well, all of these things will affect your crop. The type of crop you plant will affect your yield. The variety of grain you plant will affect your yield, and so will your fertilizer. So I would thought, well, did I read this question wrong, or did I copy it over wrong? Like, is this more than one? And the answer is no. The correct answer is E. So now that you know that it's E, why were these two not the right one? Like, how come fertilizer is the one to use and not the other two? See if you can figure that out. And pause if you're really going to try and you need more than a second. So here's the reason why. Type of crop and variety of grain are categorical variables. And you can only perform linear regression on two quantitative variables. So E is the only one that has a variable that we can control that is quantitative. So overall, I felt like that was a really, really good question. Okay, for this last problem, I was going to have us go through and do all of it. But I think maybe let's just do part D. I think let's just do part D together and skip the other ones. So part D. A scientist constructs a linear regression model for this relationship. Sorry, I read that weird, but this line has to do with this data. So I guess we better get familiar with what this data is. Animal waste lagoons and spray fields near aquatic environments may significantly degrade water quality and endanger health. The National Atmospheric Deposition Program has monitored the atmospheric ammonia at swine farms since 1978. The data on the swine population size and the atmospheric ammonia for 1 decade is given below. So we're seeing, is there a relationship between how many pigs are in the area and how much fart smell is in the air? So the reason that fart smell is because your body releases ammonia when you fart. So they are atmospheric ammonia. Wherever there's high atmospheric ammonia, it's probably really, really smelly. This is an example from the AP board, and the teacher that teaches this for the AP board, I think, plots this as number of swine and poop in the air, amount of poop in the air. Like, literally, I think that's what he uses. So, to model this relationship, we have this line. And we can see here that there is a positive relationship. So let's make sure that we know what we're looking at. We have population size in the thousands for our swine. So that means that this relates to a swine population of, I believe it's 1,850. And then atmospheric ammonia is in parts per million. Okay, so predict the atmospheric ammonia concentration if the swine population was 200 and comment on whether this prediction is reliable. Okay, so first let's make our prediction. We have y hat equals 0.127 plus 0.133, and then the population of the swine was 200. Well, up here, they have it written as a decimal. They don't have it written out in long form. So we have to change 200 to the appropriate x value. So this x would be 200 divided by 1,000. And that would give us 0.20 or 0.200, whichever you prefer. So that's what we should plug in for x. So we have to change this 200 to a decimal because that's how it's written up here. So this predicts that our atmospheric ammonia would be 0.1536. So is this prediction reliable? Well, back in our notes, the last thing we left off on was extrapolation. And right here I have this word reliable. What makes this reliable is that it was the value we predicted was inside our observed data set. So we got to ask ourselves, is a population of 200 in our observed data set? Well, let's go up here and check. Our highest population was 1,850 pigs. And if we look at this table, we can see it increases every year except for 1995. Is that true? No, it increases every year. Yeah, so this increases every single year. So that means this is our minimum value. This is 0.38 times 1,000, which gives you 380. To change it to a decimal, we divide it by 1,000. So to change it back, we multiply by 1,000. So we have data collected for atmospheric ammonia when the swine population is between 380 and 1,850. And we have made a prediction for a swine population of 200. Is that reliable? And the answer is no. So we're going to say this prediction is not reliable because we are extrapolating. How do I know we're extrapolating? Because, like I said, 200 is outside the years that we have data for. Or sorry, not the... Well, I guess you could say the years. 200 is not a population that we have observed. That's a better way to say it. 200 is not a population we have observed. So now let's use our sentence frames. We only have data for swine populations now I gotta look at my paper for swine populations between the observed values for swine populations between the observed values 380 to 1,850. We only have data for the swine populations between the observed values 380, I guess and is a better word, and 1850. We don't know if the linear pattern, sometimes they also call that a trend. We don't know if the linear pattern or trend continues for, okay, now I need to rely on my phrases to memorize. So I'm a little bit off. We don't know if the linear pattern will continue beyond, okay, our largest x value or smallest. So we don't know if the linear pattern continues for populations less than 380. So I had to make a couple of modifications to our phrases to memorize. So one is, the sentence is slightly different. Here it says, we don't know if the linear pattern will continue beyond the largest x value. And I said, we don't know if the linear pattern continues for populations. And then I needed to be clear that it was below our minimum value. So we don't know if it continues for populations less than or below 380. So it was harder for me to use the phrasing, we don't know if it'll continue beyond 380. That sounds like more than 380. The other thing that I changed was I didn't add in this statement here that says, so we would be extrapolating. I didn't add that in because we already said that at the beginning. This prediction is not reliable because we are extrapolating. So then I just used the rest. And once again, before we end this lesson, there's not just one way to say you're extrapolating. Some big takeaways are you need to address that it's not reliable and you need to use the word extrapolation. You don't have to use the sentence frames. You just need to communicate accurately that the prediction is not reliable because 200 is not one of our observed values. So that is that. Your can you do is pretty short. I'm not 100% sure if I'm going to make a video for your can you do because the can you do is so short. The video would probably be only 5 minutes. But there is one problem that I think you guys might want a little bit of explanation for. So if you don't see a lesson video and you just see a PDF of the solutions, that's because I decided that you guys were probably fine without the video. So as usual, if there are any questions on this, especially if you are a virtual learner, make sure that you let me know, email me before your quiz next time.